Well, good afternoon, everyone. I'm Jubin Thomas. I work as a technical architect at Signet Jewelers, and I'm also a senior member of IEEE, having 14 plus years of experience in supply chain and retail. First of all, I would like to thank all of you to be part of this talk. I really appreciate it. And I want to thank all the organizers of Lambda Conference to invite me as a speaker. The topic which I want to discuss today is optimizing omnichannel order fulfillment with AI and advanced analytics. And before I move on to talk about the use of machine learning in supply chain, I want to talk a little bit about OMS, which is basically the order management system, or it is also called as the order fulfillment system. So this system or this product basically takes the customer order, any order coming from any channels. The name Omni, it basically shows that it can accept orders from any channel. So basically the channels are store, online, mobile, kiosk, or call center. And it integrates with multiple inventory sources like store, warehouse, supplier, or marketplace. And basically the system has a lot of fulfillment rules and orchestrating rules within itself. And with the help of that, it is able to deliver the customer orders to the customer preferred store, or to the customer address, or to the collection point. Now, some of the major players which provides this product is basically IBM Sterling Commerce and Manhattan. And I have used IBM Sterling Commerce, and I've implemented Sterling Commerce for many retailers over the period of time. Now, though this monolith giant has a lot of benefit, and it provides a lot of benefit to the retailers, but it still have its own challenge. And one of the challenges which I have listed over here is real-time inventory visibility. And what I mean by having the issue with real-time inventory visibility is, imagine that you walk into a Walmart or a Target store, and you look out for a product. And when you look to the product, you see that, okay, you visited that store, say, for weeks and for months, and you see that the product is actually lying there in the aisle, say, for months. That means the product is actually overstocked at that store. But at the same time, if you walk into another Walmart store or a Target store, and you see and look out for the same product, and you see that the product is actually missing from there, and you don't see that product there, that means that product is actually understocked in that Walmart or Target store. Now, in a non-AI world, it is pretty hard for a retailer to manage that kind of inventory visibility, because they don't have the machine learning systems within them. And that is why machine learning plays such a major role to have that kind of integration to provide that real-time inventory visibility. Now, I'm going to talk about all the topics related to machine learning, and I'm going to basically show use cases which are small-scale use cases. You know, the real-time use case for a retailer has training data which will be in millions of records, you know, the millions of records in that. But for this use case, I've taken a training data which is pretty small in scale. It is like kind of 10,000 records, but it will give us a fair understanding how we can build intelligent machine learning systems for supply chain. So the agenda for my today's talk is building a central inventory visibility system using AI and predictive algorithms. Then I will talk about using machine learning to optimize order sourcing and routing. And finally, I'll talk about predictive analytics to allocate omnichannel inventory dynamically. And as I walk through with these topics, I will show the use case and the code snippets which will help us to understand how we can go about building these systems. Moving on to the first topic, building a central inventory visibility system using AI and predictive algorithms. Now, to have this system in place, there is one of the major system which a retailer should have, and that is called as forecasting system. And there are two major forecasting systems in the world of supply chain. One is called as demand forecasting. The other one is supply forecasting. Demand forecasting is basically a forecasting system which forecasts the demand between a store and an item combination. On the other hand, sales forecasting is a system which basically forecasts the future sales for the retailer. And moving on to the use case. Now this is the use case which I was talking about. Let me expand a bit. Now this is the sales data for an imaginary company which I am going to talk about over the period of time in this presentation. I have an imaginary retailer called Company A. Now Company A wants to build a sales forecasting system, and that is my use case. And we have the transactional sales record of Company A, and in that the key columns are the transactional date and the sales quantity. So our intelligent model based on these two columns, it will be able to predict the future sales for the retailer, and we're going to see how it will work. So I have used a time series model. They are one of the most powerful models provided by the Python framework, which helps to forecast. And they are basically the ARIMA, SARIMAX, and the exponential smoothing. I've used these models to do the prediction. And this is a high-level architectural diagram what I have, and I'm going to explain that very clearly. So regardless whichever model we are trying to build, or whichever system we are trying to build, whether it is a forecasting system or whether it is a predictive system, the steps pretty much remains the same. When I say the steps remains the same, which basically means that if a retailer try to approach this solution, or if they want to reach out to a company or a service provider which can help them to build this system, the first thing what they would ask is to provide the historical data. And now here, in this case, the historical data was the CSV file which you saw in the previous slide, and that has the data about all the sales records for the retailer A. And using that historical data, we go to the next step, which is basically the related data, and this step is also known as EDA, which is exploratory data analysis. So at this point of time, we try to analyze the data by using a lot of visualizations like plotting the histograms and Pearson correlation metrics to understand the data much clearly. And once we have that in place, the next step is basically to push the data to our machine learning algorithms, which is basically ARIMA, SARIMAX, and exponential smoothing. And once we have this in place, we try to call the forecast method of the model, which will actually forecast the records for us. I want you to have a look into the high-level flow diagram here. ARIMA model works on the concept of PDQ, and they are pretty important for ARIMA model to work. And ARIMA states, ARIMA is basically auto-regressive integrated moving average model, ARIMA, and it works on the concept of PDQ. I am going to talk about what PDQ is in the next slide. But basically, once I build the model, and when I call the forecast method over here, at this point of time, the model will give me the output of all the forecasts. And when I have that output, that is when I kind of decide whether I'm okay with that or do I need to adjust the model parameters a bit. And again, we try to fit the model and do the forecast. And if you look, this is a constant loop. It will keep on going. The reason for this is basically we have to make sure that we feed regular sales data to the model. And based on that, the model gets its continuous improvement. So you can ask me a question that, Jubin, how can we identify the PDQ value? You said that ARIMA model needs the PDQ value. How can we identify that? Is it kind of a trial and error, or what exactly it is? Because at this point of time, the only thing what I have is basically the training and test data. With that, how would I identify what is the best PDQ value? Luckily, the Python framework provided by ARIMA, or ARIMA basically have an option of running the auto ARIMA process. And this is a process which actually runs on our training and sales data. And when we run that, it basically starts with the default value of ARIMA, and it keeps on going, and it will take some time to figure out which is the best PDQ value. And it finally gave me the best PDQ value as 501 as the best value, and it gave me mean absolute error of 2.67. Now I'm going to talk about mean absolute error in the next slide, which is a very important concept in machine learning. And the mean absolute error, or MAE, is the factor which helps us to identify whether the model's performance is actually good or should I look out for some other models. Now this is a code snippet. So as I was talking, first thing is that we load the training data. And once we load the training data here, I'm kind of converting the transactional date into the date time format. And then finally, the index frequency, I'm setting it to D because the data what I have is kind of a daily data. So that is why setting the frequency as D basically means that I am setting the frequency as a daily frequency. The second step was the EDA, where we try to plot the histograms and the correlation metrics to understand the data much clearly. Once we have this in place, we finally define and fit the model. And this is where we use the parameters. We use the parameters 501, and we try to train the model based on that. Finally, we call the forecast method of these models, which will help us to forecast. And I wanted to look at this length-wide test, which basically says, I want the model to generate the set of records what I have in my test data. So model is going to generate the same number of records, or it is going to forecast the same number of records what I have in the test data. And finally, we have the forecasting method in place, and the model will forecast the values for me at this place, and it also print the mean absolute error and the Pearson correlation metrics at this point of time. Now moving on to the results, and this is where the things get interesting. And if you look into this, the ARIMA model and SariMax and exponential smoothing, it basically generated a set of 20 records because I had 20 records in my test data, and that's why it generated these 20 records, and finally it gave me a mean absolute error of 1.8. Now I'll try to explain what mean absolute error is. It is the difference between the value which was there in the test data minus what the model has predicted. And the difference between these two is actually the mean absolute error. And in this case, it is 1.84 for ARIMA, which means it is 1.84 unit off from the actual test data. Similarly, the SariMax has generated 2.54 and exponential smoothing as 4.16. So out of all the models, ARIMA model seems to be a perfect fit for my given training and test data. Now, it would not be the case for all, because it completely depends on the training and test data. For me or for company A, the use case for company A, ARIMA models works the best, but for any other retailer with a given set of different training and test data, it could be different. And that's why it is very important that we run various models and try to understand which models works the best for us. And moving on to the second topic, using machine learning to optimize order sourcing and routing. And this is a topic which is pretty close to my heart because I work very closely in forming the sourcing rules and routing for the retailers. And I'm going to talk about both of these. The first one is the predictive delivery date, and the second one, sourcing and routing. Before I speak about the predictive delivery date, I want to talk about estimated delivery date. And I believe most of us are here online shoppers. So if you are online shoppers, you would have actually seen a date displayed in your products page. And that date basically says the lead time which it will take to deliver the product to customer. And this is pretty important. I'm going to talk about this in the next slide. Now, the way how this date is calculated in a non-AI world is basically the business, the retailer's business will try to understand the lead time between the node and the carrier, the lead time taken by the product, and the lead time of the carrier. Based on these factors, when I say carriers are like UPS, FedEx, and you just name it, like different types of carriers. They have their own lead times. Based on those lead times, it gets us a lead days, which would be added up to calculate this estimated delivery date. So when I just mentioned about all these things, you would have understood that this date which is shown on the products page is actually a vague date. And the challenge with this is, when you look into the actual delivery data for the retailer, that means that the actual shipments for the retailer, you would find that the actual delivery date is way lesser than this estimated delivery date. Now you would have understood the problem here. So it is so important for a retailer to have this date, a near to accurate date, which will help them to understand that whether their business is going to increase because of this date. The second one is the sourcing and routing, which is basically finding out or figuring out the best store or the best warehouse which can fulfill the needs for the customer or fulfill the customer order. And to build this use case, I've used two models, which is random forest regressor and k-neighbors classifier. They are again two different models provided by Python framework. And I'm going to talk a little bit about this. So the way how random forest works, as the name says, it's a forest model. That means it kind of generates a structure of forest before it predicts the value. And the second thing is the random state as 42. So in the first model, like the ARIMA model, you saw that it works on PDQ, and that is something important for the model. Here, for random regressor, the N estimators and random state are two important factors which are required for this model to work. And the way how it works is that random state 42 means that regardless if I'm trying to hit the model with the same input, my model will return me the same output regardless how many times I'm going to call it. That is why I need to pass random state to this model. And the second thing is the N estimators, which basically means I pass the value as 100 over here. It basically means it creates 100 decision trees and finally ranks the best combination to give me a predictive delivery date. The other hand, I have k-nearest neighbors model, which works slightly different from random forest. The way how it works is we need to pass the parameter n neighbors equal to 5, which basically means based on the input what I provide to the model will try to fetch the 5 nearest neighbors in my training data, which looks kind of similar to what I am passing in the input. And based on that, the model will return me a predictive delivery date. And I believe everybody have actually seen the screen. I rarely think that you wouldn't have seen the screen. This is Amazon's products page. And the date what you see here is actually the estimated delivery date. Now, according to one of the article which I read, in one of the e-commerce article which I read, 47% of customers, they abandon their carts just because this date, the estimated delivery date, is not matching their expectations. That is why it is so important for retailers to have this date near to accurate. Now let's talk about the use case. The first use case was the transactional data or the sales data for the customer. Now this use case is basically the historical delivery data for the retailer. Now, when I say delivery data, that means that it talks about whether the order was successfully delivered by marking it as fulfillment success as 1 and 0 for it was not a successful delivery. It has the inventory value displayed over here. But I just want to talk about the key variables here, which is basically the customer zip code, the store zip code, which basically fulfill the customer order, the order quantity, and the shipping option. Based on these key features, and this is the training data which I'm going to pass to my model. Based on these key features, let us build a use case or basically a predictive model for our company A to predict the delivery date for company A. Moving on to the code snippet, the first thing is basically to load the data, training data, and the US zip codes. US zip codes is available in the USPS websites. And if you look into this, I have dropped the key features from the data frame, which is customer zip code, store zip code, and fulfillment success. And there are two variables which I want to show you here, the X variable and the Y variable. And this is what we use to train the model. So the customer zip code is something which is important for this model to run. And now based on the input, this is where we pass the input. I have passed the input as requested quantity as 10, shipping option as standard, customer zip code as 80517. By the way, 80517 is the zip code of Holiday Inn. Based on these inputs, the model was able to predict the values for us. Okay, so let me go quickly there. Based on shipping option what I provided as standard, it figured out that the nearest store is 89402, which is in Crystal Bay. Distance to the customer is 767 miles, and it is able to deliver the customer order and gave me a predictive date of 5/13, which is kind of 6 days off from today's date. And the reason why it gave me this date is because of the training, what it has achieved based on the training data. And similarly, there are other things which I would like to show here. And when I try to pass an inventory higher than what is there in the training data, it gave me a message, no available inventory for item 2 at any nearby store. So yeah, that's the use case for a predictive model. And moving on to the last topic, which is predictive analytics to allocate omnichannel inventory dynamically. Now you remember the second slide which I showed you, which showed basically the problem statement of real-time inventory tracking. Now that's an actual problem for a retailer. Now we are trying to solve that problem with the help of machine learning. And I'm going to show the use case here, not just the slides. I'm going to show a demo which I've actually prepared here. And let's help this fella, the poor fella who is worried about the overstocking and understocking issue, by providing a solution to him. So the first use case was the sales data, second one was the historical delivery data, and finally this, what you see here, is actually the product data, the product and revenue data for company A. And we are trying to build an intelligent system which can tell what kind of inventory status or quantity it has to maintain for a store. And the way how it works is it gets the input, does the data validation. If it fails, it displays the error. Otherwise, it basically model predicts the inventory level to be maintained and the mean absolute error which has to be displayed. Moving on to the demo. So I'm going to use the same thing, the same data, what is there in my training data. So for example, the product ID 30. So I'm going to give the same product ID here. And the product cost as 275, product revenue as 5784. And the days of the week was Tuesday, I believe. So one for Monday, 2 for Tuesday, so on and so forth. And it was not a holiday, and the expected delivery date, I give it a 7, which is exactly the same in the training data. Now when I click on predict status, the model is able to give me a count of 23 inventory counts to be maintained, which is pretty much similar to what we have in our training data. And it also gave me a mean absolute error of 0.3, which is kind of closer to 0. One thing I forgot to mention is mean absolute error, the more it is closer to 0, the better is the performance of our model. Now at the same time, if I try for my store, for the same product, same price, if I basically say that, okay, I want to have a revenue of $10,000 for the product 30, with pretty much everything else the same, it basically gives me that I need to maintain the quantity of 41. Again, if you look into the MAE, it is basically 0.48, again pretty closer to 0. And regardless how many times I pass the same input, it is going to give me the same value, and that's the power of random state when I passed that to the model. See, I'm giving the same input again, revenue as 10,000, and Tuesday, expected delivery days as 7 days. When I click on predict status, it gives me the same value, and that's the power of putting the random state. So I hope you liked the demo here and my talk, and that's pretty much which I want to share. Let me see if I have anything else to share. Yes, that's pretty much it. And time for questions. If you have any questions.
So how are you making use of the k nearest neighbors alongside the random forest state? How does the KNN aid the random forest?
Both work separately. So both are different models. So let me try to. So even in the first use case, I was actually talking about 3 different models.
In the demo, we have made use of the random forest.
Correct, yes.
But the same thing, what is the mean absolute error difference between the KNN and the random forest?
They both will be different. I don't have that in my slide, but when both the models run, they are going to give you similar. So in this case, it was actually pretty closer. That is why it was able to give the same predictive delivery date. Okay. And I actually ran a lot of models, and based on all the models which I ran, these 2 models were the perfect fit for me. That's why I used these 2 models in my presentation.
So out of KNN and random forest state, you got better results with random forest?
Both were same. That's why I kind of put it. Yes. Yes.
In these kind of systems, how often do you have to retrain the models?
Yeah. So the question is that in these systems, like supply chain systems, how often we have to retrain the system. So the answer to the question is, we always need to train our models. That means, like the first use case was the use case of the sales, historical sales data, and we were building the sales forecasting system. Once the model is ready, we still need to constantly provide the daily sales data coming into the system, and that is how the model gets improved by itself. And second one was the predictive model. Again, that depends on the delivery data what the retailer has. So the delivery data has to be constantly fed. That means the shipment data has to be constantly fed, which will have the actual delivery date, and that's how the model gets improved. Yeah. Any other questions? If not, thank you so much, and let me just pull up the last slide, which will have my details. Yep, so that's my email ID, jubin.thomas@ieee.org, and that's my LinkedIn, contact Jubin Thomas, and that's my GitHub repository. I'll be more than happy if you can reach out to me, and if you have any questions related to supply chain, I'll be more than happy to answer you. Thank you so much.